in the physics department of the Professor Mark Bucket. He has been a postdoc fellow in the physics department of the University of Warwick and the University of Oxford. He is currently professor at École des Ponts, a deputy director of the Atmospheric Environment Research and Teaching Center, CERIA. He works in the fields of data assimilation, machine learning, inverse problem, and dynamical system in the geosciences, with applications to atmospheric chemistry as well as in environmental statistics. He develops new mathematical methods to better estimate the state of the atmosphere in the ocean and their constituents using large sets of observation and complex models. He is a fellow of the European Center of Medium-Range Weather Forecast, an editor of the Quarterly Journal of Royal Meteorological Society, foundation of the Science and Frontiers in Applied Mathematics and Dynamical Systems. Please, thank you very much, Professor Mark, and it's up to you.
Okay.
We are waiting for your presentation. Thanks.
Yeah. Thank you very much, Aldo. Thank you very much for organizing this course on data assimilation. So the subject that I was assigned is this hybrid method, whose goal is actually to combine the best of what the Ensemble Kalman filter method has to offer with the best of what the variational method have to offer. And this is something that one word of caution is maybe the fact that I haven't been working on the field on this specific topic for about 4 years now, because of this, the machine learning tsunami that we had to switch gear and change subject. However, this is, I think, a very, very interesting subject, because this is really, you need to know a bit of data assimilation, and hopefully over the past couple of years, you've learned already quite a few things in data assimilation. And so it really, depends on the fact that you should be aware of some of the advantages and drawback of both types of method to actually enjoy combining them and try to build new methods that are getting really the best of those two sets of methods. And so this is also the kind of fun game, because this was over the past, let's say, 30 years up to maybe 15 years ago. It was not so, I mean, people were at least trying to implement those basic data assimilation method, and building those new methods with new mathematical ideas or new algorithm. It was not so common, actually, and people didn't really dare trying that kind of method, except for the variational method on one side, and then trying to build on the Ensemble Kalman method on the other side. But at some point, I mean, the community really realized in the geophysical data assimilation, at least, that they really tried. I mean, they could afford trying to merge those techniques and trying new types of maybe a bit more sophisticated types of method. And it wouldn't necessarily mean that it would be more numerically costly to actually use those methods. Those methods were actually could be implemented in operational centers, so typically in numerical weather forecast centers. And so it's fairly recent. It's like maybe 17 years ago that those type of methods have been started to be investigated, and maybe less. And the hype about it was, however, really moved on only 10 years ago. So that's still a very active topic. Okay. So first things I'm going to do is that I'm going to summarize some of the things that you've seen on the Ensemble Kalman filter. And it's a quick summary, because this is going to be, the rest will heavily rely on this. And also to set the notation to be sure that you follow me in since this topic is a bit more technical. So first of all, so this is a diagram that actually summarizes the I mean, this is not, you don't have, there is not everything in this diagram, but this is the way I see things, and some of my colleagues as well. It's the family of the Ensemble Kalman filter methods. So it's very likely that with Takema Yoshi, you've seen the Ensemble transform Kalman filter, and this is the one that I'm going to use as well. But basically, so the NKF is split into two types of algorithms. So one is the historical one, the original one, the stochastic NKF. This is the one where you perturb the observations to get the proper uncertainty on the posterior ensemble that you build in the analysis. And there is the class of the deterministic ENKF, and those are essentially square root ensemble filter, because the goal is to avoid perturbing the observations. So this is purely deterministic. There is no stochasticity in it. And then you've got different classes of way to carry out this analysis. So depending on the space that you want to favor, actually, in the whether it's the observation space, the state space, or the ensemble space. So the linear algebra will be carried out in different spaces. So essentially, all of the methods are, at least in very simple context, all of those methods are equivalent. But at least from a mathematical standpoint, but from a numerical one, their cost will depend on the space where you carry out the algebra. So you've got those ensemble of families, like so the ensemble square root filter, and so when it was more or less introduced by Jeff Anderson under this name of ensemble adjustment Kalman filter. And there is a variant where you only need, you only use one observation at a time. You carry out an analysis one observation at a time. It's not necessarily inefficient. It's just that there is a sequential update with those observations. And this is essentially the same as the one that I mentioned earlier. And this is called the serial ensemble square root filter. And there is the one where you carry out the analysis mostly using linear algebra in the ensemble space and trying to take advantage of it. And this is called the ensemble transform Kalman filter. So those are essentially the couple of the three types of subclasses of deterministic NKF. And there are also a lot of variants of those techniques. And one of them, for instance, consists in combining the ideas of the stochastic one with the idea of the ensemble square root filter. And this is called the DENKF, whose actual name is deterministic ENKF, but this is very confusing with the fact that it belongs to the class of deterministic ENKF. But this one is actually is an approximate ensemble Kalman filter, and it's used, but it's very practical to use with large models. It has a lot of interesting features. That said, as I mentioned, there are many other types of variants, I should say, of ensemble Kalman filter, and there are also ancestors of the ensemble Kalman filter, like the reduced square root Kalman filter, like the SEEK, ancestor Kalman filter, and so on. So there are many papers actually in this family. Anyway, this was just some kind of reminder, or maybe going a bit further, I don't know. This is the kind of filter that we tend to play with. So this slide is only about notation. It's really to tell you what kind of notation that I'm going to use. So because I'm going to consider hybrid methods, there will be an ensemble and a variational method, and they will be blend together. So first of all, we need an ensemble. And so the notation that I will use is this ensemble of state vector, x1 to xne, and ne is the size of the ensemble. So that's pretty obvious. And you know that in the ensemble Kalman filter, we tend to think, we don't necessarily have to write, but we tend to think of the mean of the ensemble, and that is usually easy to compute. So this is this x bar, and here the EF is for the forecast, for instance. And the error covariance, the forecast error covariance matrix, PF, is approximated by the sampling formula, the empirical formula, which is this one that I'm sure you have seen already by now. We don't necessarily have to compute it, okay, but implicitly, this is what we actually assume. Okay. And this matrix can actually be, this formula, sorry, can actually be, and this is actually a matrix, can be factorized into this, okay, using this X matrix, which is the anomaly of the perturbation matrix, which is the collection actually of perturbations which actually built this error covariance matrix. So this is some kind of factorization. I don't call it because it's not consistent with the mathematical vocabulary. It's not consistent. It's not a good thing actually to call it a square root, even though many of my colleagues do call that a square root. It's not really a square root in mathematics. This is just a factorization, like a Cholesky factorization, if you know the Cholesky factorization. And so the collection of the columns of this anomaly matrix is those, so I've chosen to be normalized here. So this is just the departure of one member of the ensemble minus the mean of the ensemble and divided by the square root of any minus one, so that the multiplication of x with the transpose of x will give you the empirical formula for the forecast error covariance matrix. Okay, and you can build other types of anomaly and perturbation matrix, like for instance the one corresponding to the analysis. And so this is exactly the same kind of formula, but applied to the analysis. Okay, so those are the main notation that I'm going to use, and I'm going to use a lot of this X anomaly or perturbation matrix. So just keep that in mind. So if there is a pressing questions, I mean, I think you can really interrupt me. I'll try to answer if this is if there is a fast answer. Okay, so I'm going to just give a summary of one of the key variants of in the Ensemble Kalman filter, because this is the one that I'm going to use in the following. And so this is the ETKF. I'm pretty sure Takemasa Miyoshi used this one as well. And so the idea in the family of all the ENKF methods, the idea is actually to carry out the analysis, but within the space generated by the ensemble. So this is a subspace of the state space. And you can parameterize any state vector, projecting into this ensemble space using a set of coefficient W. Okay, and using the prior of the anomaly matrix, and you actually give a weight to each one of those vectors, and this is some kind of a family of vectors that defines a coordinate system for the state. Okay, and instead of solving the full thing like the Kalman filter would do, you solve it within this, as we call, ensemble subspace. And then the solution of the analysis is written, can be written using linear algebra within this ensemble subspace. And the solution is this one. And the nice thing about it is that the inverse matrix that you have to compute when you compute the Kalman gain is actually carried out within the ensemble subspace. So the dimension of this identity matrix is NE times NE, which could be small. Okay, and delta, as usual, is the innovation vector. Okay, also another notation is this Y. Is this YF matrix? So Y matrix is just the composition of the observation operator with one of the anomaly matrix. Okay, so this is just a simple notations to make formula even shorter. For the perturbation update, you can also express the whole update using the ensemble transform, and the set of perturbation, and this is the nice thing about it, is given by this XA perturbation matrix, and it's given by this formula, which actually act on the perturbation matrix, the prior perturbation matrix, and it acts on the right using this transformation matrix T, which is defined within the ensemble subspace, which makes it usually a small matrix. Okay, just a dozen of dimensions. So typically, let's say it's a 50 by 50 matrix. So that's a small one, and you can carry out linear algebra within this subspace in an easy way, and it's not really costly. Okay, and then you can recompose the full set of vector of the updated ensemble. So using this the updated the updated analysis. So the analysis for the state and the set of updated perturbations using the T matrix, and you can so each one of the updated ensemble is defined by this formula. Okay, so this was a summary of the ETKF and the main update for the ETKF. A few details that because usually it's not sufficient to have one which works very well, at least on low order model. You need also to have some to impose some constraints on the T matrix. For instance, the fact that the vector of 1, okay, defined in the ensemble space, is actually an eigenvalue of the T matrix with, say, eigenvalue 1. An eigenvalue 1, so it's an eigenvector of the T matrix, which has to be actually 0. I'm not saying it's a 0, sorry, the eigenvalues, because the any solution of the update of the perturbation matrix actually is given by this XFT, but also you could apply any unitary or uni-orthogonal matrix on the right, and it wouldn't change the solution. So you need to impose some constraint on T and U so that actually the anomalies are centered, so that when you have the anomalies to the mean update, you don't actually introduce a bias in the mean. So this is just a constraint to center the ensemble onto the mean. Okay, the updated perturbation onto the mean. This is just a very small, easy technical point, but this could be important actually to get a good accuracy. Otherwise, you introduce a bias. Okay, so one of the, I'm pretty sure you've seen that one already, but one of the key low-order model that is used a lot to illustrate data assimilation method and to maybe sometimes develop new schemes, and it's always important to start with a low-order model. It's this Lorentz one-dimensional 96 model, and it's so as I said, it's a one-dimensional model which corresponds to the mid-latitude zonal circle, okay, of the global atmosphere, and it's it kind of represents the it tries to represent the Rossby wave in this mid-latitude circle. And so those 0 to 39 actually index corresponds to the space dimension, the one space dimension. And there are also 40 variables, and there's spatial variables. And on the x-axis, this is time. And so you see a typical simulation for this Lorentz 96 model, and you see those waves, which are meant to be those Rossby waves. And it's a nonlinear model, and it does have it is chaotic, and so representative of what's happening in the atmosphere. And that's why those waves are actually they are not linear. They are nonlinear, and they do interact. And the patterns that you see are really difficult to predict because the system is fundamentally chaotic. Okay. So this is these equations, and there is this nonlinear advection terms, and there is a dampening term, and there is a forcing term that injects constantly energy or draws out energy from the system. And so it's a system that is well known, well studied, and it has 30 positive Lyapunov exponents, which are the ensemble directions, and one neutral one, and the rest is dissipative. Okay, so this is the typical numerical result that we have on the ensemble transform with the ensemble transform Kalman filter, and you would get also similar result with a well-tuned square root, deterministic ENKF. And so when you, this is the a synthetic experiment with this model, and you compute the analysis root mean square error. So this is the error that you make in carrying out data assimilation, carry out this ensemble transform Kalman filter. and you compare this score with the ensemble size. And so you make a lot of simulations to actually get that. And you have to implement those techniques that I'm sure you've discussed already yesterday. It's the inflation and localization, because those are the two tricks, but it's a bit more than that, that are necessary to actually use an ensemble Kalman filter in an efficient way with high-dimensional models. Okay, so localization is the most important one, and inflation would make some additional correction. So if you don't do that, if you don't implement localization and inflation, you end up with this a blue curve here, with a score which only gets nice when you've got a very large ensemble size, which is, of the order of the size of the system. And obviously that's something that you won't be able to do with a large model, with a big physical system to play with, because it requires the ensemble size to be of the size of the dimension of the state space of the system. So this would be crazy to carry out such a thing. So you need to implement localization. If you only need inflation, so inflating the ensemble, so have to account for unaccounted errors in the system, then you will end up with this violet curve. But if you really account for localization, then things get good, and things get already good as soon as you have a reasonably small ensemble, like 5, and you already get a score which is viable, which proves that your data assimilation technique actually works. And of course, if you still increase the ensemble size, you get even better accuracy, but still it's nice. And if you implement on top of that, on top of localization, inflation, it gets even better, and you've got this green performance curve where you're already good with an ensemble size of 5. So this is just to illustrate the fact that first, the ensemble Kalman filter are viable method with chaotic dynamics, and second, that you would still need to use those localization and inflation method to actually have a viable method and have a good accuracy. I think it closes this this summary thing, because this is I'm not going to summarize the variation method because this maybe is less tricky, but of course this is going to be discussed in the following. Now I want to move up in some of the technique that have been proposed, where it's more people from the ensemble Kalman filter side who wanted to, weren't necessarily acknowledging that, they wanted to implement some of the ideas of the variational method. And one of the key ideas is the fact that you'd like to assimilate asynchronous observations. So those are the observations that don't really fall into this analysis time that you have in the INPE, because this is really one of the drawbacks of the ensemble Kalman filter, is that you have to carry out analysis at some specific times. Whereas with the let's say 4D var, you can assimilate observations that are actually coming from different times or dates, and you can as long as they are within this the variational data assimilation. Okay, so one thing to actually make the ensemble Kalman filter better, to account for observations that are not only given at one specific time, is to use this smoothing idea. So smoothing idea, a smoother in data assimilation or in applied mathematics, is a technique that is estimate, like in data assimilation, a state vector, but using observations that are possibly coming from the past, from the present, okay, like an INPE would do, but also from the future. Okay, so another way to see that is to try to look in the past and try to improve the state of your knowledge of the state of the system in the past, knowing observations up to present. And so those observations would be future observations for the past estimation. Okay, and this is extremely useful in the so-called reanalysis, that people can sometimes carry out in numerical weather operational center, so that they can, using all the observation that we have accumulated over the past decades, they can actually update and make a whole simulation using data simulation and those types of smoother. They can really have a better accuracy on the estimation of the full trajectory of the atmosphere. And they can provide those reanalysis products that are extremely useful for everybody in the geophysical community. Okay, so you can build actually a smoother from a Kalman filter on an ensemble Kalman filter, and actually the Kalman smoother. So without talking about ensemble, as was known in the engineering and applied mathematical community for a long time. And it was introduced in the geosciences by Steve Cohn a long time ago, at least for you. It was maybe 25 years ago. And Peter Jan van Loven, actually, who is going to talk next, has also adapted this idea to the ensemble Kalman filter world. Okay, so trying to make smoother out of an ensemble Kalman filter. And okay, one way I'm going to try to explain the concept in an easy way. It's a bit okay, without going into too much formula. One thing that you have to know is that all the formulas that you've seen about the NKF could actually, so the update of the ensemble, I'm not speaking about the perturbation only now, I'm talking about the updated ensemble. It turns out that you can actually write the matrix of all the new member of the ensemble with this E matrix, EA at time tk, and that you could actually write it as an update on the right of the prior ensemble, of the forecast ensemble. Okay, you could make a big compact formula where actually T would be this transform matrix, but this one would also account for the observation, because of course the update depends on the observation. So you could compact everything into this T matrix, and this is a general formula that you could be aware of. And any of the formula that I've shown earlier could be written in this form. What necessarily, here I don't want to specify what is T exactly. But the thing is that if you consider, let's say TL is the present time, then the analysis at the present time could be written actually as the forecast of the analysis using those observations from a prior time tk, and then you would write the ensemble, the matrix of the ensemble of the analysis ensemble at time tk as the update formula that I've introduced earlier. So in a very generic way, that would be valid for any type of ENKF. But then you could associate this forecast of the perturbation. So from TK to TL, you can apply it to the ensemble, to the forecast ensemble. So leaving out the T matrix, so that actually you would rewrite the updated ensemble matrix with the ensemble forecast matrix. Okay, using this matrix T, but which accounts for the observation at time tk. So this is the notion of really using asynchronous observations. So for the update at time TL, I'm using observation at time tk. Okay, and it turns out that this formula, this very, very general formula, you can also apply it when you swap the time, where you exchange TL and TK, so that actually you can make an update in the past, knowing the observation at present time. Okay, that will require to use this forecast using the inverse of, so that's a bit artificial, I agree, but still the formula will be correct. So this is you can see this formula, okay, as also valid when TL is actually prior to TK, which means that you've got a formula for updating in the past the ensemble using observation in the future, but in the future would be for us present time. Okay, so that would be actually a way to improve your knowledge of the of what was the past ensemble. Okay, and so what you can do is have a two-pass system where first you've got an INKF, okay, and you've got an update at each time steps of the ensemble, and assume that you store this ensemble. You can later come back to the ensemble at time TL, and you would use the latest observations to actually update this ensemble. So that would be the second pass where you go back in time to update the set of those ensembles, but using future observations. So using new information for the system. So in principle, on average, it should use to a better accuracy for this ensemble, a better estimation of the ensemble and the uncertainty on the system. And this is summarized by this formula. So this is the S stands for the smoothing. So it's a new analysis, an improved analysis on the ensemble, but using all the observations from time tk up to the present time, which would here be T capital K. And to carry out this this formula, you need to have those transform matrix T, and you apply those transform matrix T that only depend on the observations and so on. So that's a way. This is a very generic way to actually build a smoother. So with the ensemble Kalman filter. So first you have a first pass when where you update. You do a generic ensemble Kalman filter, okay, using the observation. You don't change anything, but that at any point you can go back in time and update your knowledge of the ensemble if you have stored them, okay, in memory or on disk. Then you can update that, use your future observation that will lead to a better accuracy for the system. But you only need those two passes, two passes actually to have a very good and viable system, algorithm. And this is the way to represent it. So this is the set of observations moving from the left to the right. You move in time up to the present time, and you assimilate. So use an ENKF and you update. So you've got a state update using the ensemble Kalman filter. And then at each time step, you can actually go back in time and use the previous, use again the previous observation to update the past estimation of the ensemble or the mean state, if you want. Okay, and this is from a mathematical standpoint, this is perfectly correct. You are not reusing several times the observations. You are just updating one estimation using future observation. Okay, and so this algorithm is known as the using the ensemble Kalman filter. It's known as the ensemble Kalman smoother, ENKS. Okay, and using exactly the same type of a synthetic experiment that I've shown in presence of inflation localization, you can actually look at the scores that you can achieve with the ensemble Kalman smoother. So, but going back in the past, because if you stay at the present time, then since the first pass, it depends only on the first pass. So it's an ensemble Kalman smoother will give you an estimation, an analysis at the present time, which is exactly the same as the one that which is given by the ensemble Kalman filter. So the score at the present time is actually the same as the one of the ENKF. But if you move back in time and you had an estimation thanks to the ENKF of those previous states, and they were obtained with this average root mean square error, still the same. But if you use the ensemble Kalman smoother with the second pass that goes backward, then you get a better estimation and you reduce the error on the estimation of the state. And this is why the curve now of the root mean square error for the ensemble Kalman smoother is decreasing. Okay, you can't actually go to zero. We'll speak a bit about that later, I guess. You can't go to zero, but you get a fairly, at least on these very lower without model error. So in this very synthetic and simplified case, you objectively see that mathematically speaking, you can get a very good improvement on the estimation of the state. So that's okay. So that's a nice thing to know. but you're already playing with time, and you've got actually the variational schemes that are lurking behind, because the even though we didn't mention variational, because we are using those asynchronous observations. Okay, so actually that's another way to see the Ensemble Kalman sniffer, is this trying to implement those within an Ensemble Kalman filter scheme, trying to assimilate those asynchronous observations. So one way to do it is to consider the variational scheme, but we won't be implementing the variational scheme. We will only implement an Ensemble Kalman filter to do so, or actually a new form of the Ensemble Kalman sniffer. And in this case, we can actually carry out this computation. So this is going to be technical, and will give you only the main ideas. It's because I have asynchronous observation, so I want to work over a time period, so a data assimilation window in time, like a 4D var would do. I want to write a cost function because I want to incorporate those observations given at different times. So this is a good way to actually write things. This would simplify the way we think about it. Would be maybe make it slightly less difficult than considering the Ensemble Kalman filter and doing sequential update. So this is just writing the cost function for this system, where you got the observation at the time step within the window. And here I'm also considering model error, but this is something I will go back at the end, but I won't necessarily use that right now. Okay, and you want to introduce the fact that you are actually working in the ensemble subspace, because I want to use the TKF here as one of the best representative of the Ensemble Kalman filter. And so I parameterize everything within the ensemble subspace, and I can do that for the prior, but I can also do that for the model error perturbations, if you do consider model error. If you don't, then you don't have to do that. But the nice thing about everything is that once you've carried out all you wrote down everything and you incorporate that into the cost function. The cost function simplifies considerably, exactly like it does in the Ensemble Transform Kalman filter. And you can write the cost function in a very simple way with this prior term, exactly like in the Ensemble Transform Kalman filter. But this set of W coefficient actually depends on not only the set of coefficient in the ensemble space at the present times, but also on the times within the window, okay, up to the beginning of the window. So this W is a generalization of what you see in the Ensemble Transform Kalman filter, but with a set of coefficients for the ensemble at different time within the windows. Okay, it's like a 4D generalization of the coefficient in ensemble space that we usually use in the Ensemble Transform Kalman filter. Okay. And the observation term still depends implicitly via this X. It depends on this set of W through those formula. Okay, this is so we can have eat a few things under the carpet here, but at least it's explicit. You can write it explicitly. And you can solve now because this is very simple to formulate the cost function this way. You can try now to minimize this cost function first theoretically and then later on numerically over the set of coefficient W. Okay, and that's very simple for the first term, which is the background. Okay, the prior, and that's slightly more tricky for the observation term, but this is something that you still can do. Okay, and so I'm not going into the details of it, but at the end I just want you to know that you've got a nice and simple formula that you can carry out at the linear order. Okay, you could work into the higher order, but this is not something I want to discuss right. I will discuss that at the end. But if you're discussing that right now, I'm just considering the linear order of it, just one update at the linear order. And you've got formulas, and those formulas are not that difficult. They are just traditional types of matrix that we can data estimation, except that they are like the TKF formulated within the scheme of the ensemble transform Kalman filter. So within the ensemble subspace. And okay, and that's the solution of it is again a way to assimilate using only an ensemble Kalman filter. You would assimilate. This is a way to, at linear order, to assimilate asynchronous observation. And it can actually be shown that this way to carry out this example is very similar to the ensemble Kalman smoother that I've described earlier. And very importantly, if you don't consider model error like I did, you just assume that there is no model error, and you only keep the rest of this formulation. So in particular, this long set of coefficient, where you got the coefficient in ensemble space, but at time, the end of the window, and then going back in time to the beginning of the window. So it's the concatenation of all those coefficients. It's still it's a bigger vector, but it's still small compared to the ensemble, the state space dimension. And when you carry out this analysis without considering model error, you end up to a method that has been proposed by the Maryland group in this paper, and this is called the 4D ETKF. So really, the philosophy is really carry out an ETKF, but instead of only assimilating observations that you got at some specific time step, the one of the analysis of the ETKF, you want to consider other time step within some specific window, and carry out an analysis which is very, very similar to the ETKF1, except that you have, stacked on top of each other the contributions for those different times within the window. But the algebra later on is the same, It's just slightly more difficult because you have stacked vectors on top of each other, and so the dimension of this vector is a bit higher. But it's nice because this is another way to do smoothing. Just from the standpoint of people working on the ensemble transform Kalman filter, you can try to assimilate those asynchronous observation. What I will show later on is that you can actually generalize that and see that this is the first loop correction of a bigger prototype scheme, which is called the iterative ensemble smoother, and which I will talk about because it really precisely, it's very, the proof of this smoother that I will talk about, and which is really a prototype of what an ensemble Kalman filter should be. It's rather simple to understand. It's really coming from bias consideration. So it's kind of a very, you don't have any arbitrary choice in the building of these types of method, and that's why I'm going to discuss that. And many other methods can actually be understood from this standpoint. But for now, I'm not going to discuss that. And we'll discuss some of the variants of the hybrid and ensemble variational techniques that have been introduced in the literature. But now, to summarize what I've just said, is that it's important to remember that people have been, from the ensemble Kalman filter side, they have been working on trying to assimilate those asynchronous observations, and so have these ideas from the variational standpoint, and this led to this ensemble Kalman smoother, to this asynchronous ensemble Kalman filter, or this 4D ETKF, and they are very close to each other, and some of them are equivalent. So even without necessarily going into variational method or speaking about a joint or anything like that, you can actually implement those some of those ideas within the ensemble Kalman filter framework. So now let's move on into the central topic, which is how can we combine ensemble Kalman filter methods, and ensemble variational technique. So I'm not going to speak about the particle filter because Peter Yan will do so in the next talk. Maybe we're going to speak about some 4D generalization of particle filter, but I'm not going to mention. I'm going to focus only on the ensemble transform Kalman filter, or any Ensemble Kalman filter, actually, for that matter. Okay, so where do you, when we look at the interest in those geophysical data assimilation methods, so trying to use them in the, at least in the field of the geosciences, where they've been introduced, okay, with the goal to use them in with high dimensional system and with big data coming from the observations. So when were those methods introduced? So this is the timeline where I've introduced. So this is the timeline of the main method that were introduced in this in the numerical weather forecast community. And the on the top, this is the more from the dynamical system standpoint. What it implies actually to use those new methods on the model. And the on the bottom, this is more like the statistician standpoint. So what types of statistical or optimization methods should I use to implement those methods? Okay, so in the 50s of the past century, you've got you first got the objective analysis, which actually led on a numerical way to the objective analysis, what people were making prediction using their expertise and their skills and using maps of geopotentials. But later on, with the advent of computing, people have been implementing that in an automatic way, so using optimal interpolation and something which is similar to 3D VAR. So carry out analysis at one given time step using some prior information, so given either by the observation per se, or given by some prior that you would have on the state of the system. So, for instance, some statistics that you have on the state of the system. And I would of course imply between each analysis to forward this the best estimation, the analysis that you have on the state of the system, using the model forecast. Okay, and from a statistical standpoint, this is just linear regression. And then later on, people have been so wanting to actually assimilate those joint observation and carry out not only a set of observations that were received at some time step, but assimilating more, and also with the wish to actually get some more consistency between the observation of the model, they developed the 4D VAR that I guess you have seen. And this borrowed from the ideas of optimal control, so in the applied mathematical community, and it was known for a long time. But from the dynamics, it also introduced the use and required the use of the adjoint of the model. Okay, and the adjoint of the model, as you know, is extremely useful in optimization. Okay, this is what allows you to compute the gradient in the 4D VAR, in the first function of the 4D VAR. So this is in an efficient way. So this is actually mandatory to get the adjoint or some estimation of the adjoint of the model. And but unfortunately, this is a very difficult technical task. Okay, and this is a fundamental one. Okay, because this also means that the people in the applied mathematics, or actually in computing science, they consider it as an interesting topic per se. It's not purely technical. It's also a mathematical topic per se. How would you derive the adjoint of a model which is implemented as a huge piece of code? How would you derive a code that actually would give you the adjoint of the model? Okay, so that's considered a theoretical topic actually in scientific computing. But for us, that's at least in the geosciences, that could be seen as a very technical detail, but a technical problem. But that's okay. That actually has drive or prevent some of the development in data assimilation for a long time. Things are changing now, but I won't speak about that. And it was at the end of the last century, and that's where people introduced 4D VAR. So, and they had to develop this adjoint model. Okay, so that's the strength. This adjoint is the strength of 4D VAR, but that's also its weakness, because you would have to develop the adjoint from a technical standpoint. But having it would allow you to compute in a very efficient way the gradient of the system throughout the window. Okay, using all the observations that have been acquired in the data assimilation window, and that's a huge strength for the optimization. Okay, and then later on there was this because part of the community didn't want to develop the adjoint and were maybe a bit afraid of the 4D, they wanted to develop this ensemble Kalman filter. So from the coming from the Kalman filtering, again, it was coming from the engineering community and applied mathematics community, and they developed this ensemble Kalman filter from the Kalman filter. And then the new notion in terms of dynamics is using the fact of using an ensemble of a forecast ensemble. So this is, again, it has a drawback and an advantage. The advantage that we will discuss is the one that we've got from the ensemble Kalman filter, is the fact that you've got a very nice estimation of the uncertainty of the analysis or of the forecast. And that's key, because this is something that it's much more difficult to obtain within a variational context. Okay, so that's, and this uncertainty depends on time. Okay, it depends on this forecast of the ensemble. So it would naturally evolve in time. And that's something which is great. And the price to pay is actually, there is actually both. It's the fact that you don't, well, at least from the ensemble Kalman point of view, the price to pay is that you need to make this ensemble forecast. Okay, so you need to make more forecast of the model with with the nice thing that, of course, those forecasts are independent, so you can carry out on a parallel system very easily. But as I already started to discuss, you've got advantages and disadvantages of using pros and cons of using the variational method or the ensemble Kalman filter methods, which led people actually to try to combine them to get the best of both worlds. Okay. And we will see that this is something that we can do to a large extent, not entirely, but to a large extent, we can actually do so. And so those ideas, trying to mix things that was carried out very early, well, 20 years ago, I mean, no, 15 years ago. But the implementation and the interest of in numerical weather forecast community and the implementation in numerical weather forecast was only done like 7 years ago, 8 years ago. Okay. But the method per se, they were introduced earlier. But those are the dates corresponding to the use in numerical weather forecast centers of those new methods. Okay, so this was the historical picture, and maybe some motivations for it. So one of the first thing maybe to mention where people were trying to combine these ideas. First, I'd like to discuss a bit the word hybrid. So hybrid is used a lot in data assimilation in many different circumstances, in many different contexts. Here it's already not so easy. I mean, there is something to mention is the fact that I'm usually not using the word hybrid to discuss this combination of ensemble and variational method. I prefer to use just ENVAR. Because hybrid was actually used for the, it's really hinting at the fact that you want to combine ensemble method and variational method, but focusing on building the background covariance matrix. Okay, and this can make very concrete. Because this was a suggestion, so 20 years ago by Amil and Snyder to actually combine the climatological or the static actually background covariance matrix that you would use in 3D var and actually also in 4D var, but at the time this was they were focusing on 3D var, and this is the C matrix. So it has it's not time dependent, so in that sense, it's not so good, but it's a full rank because you've got a pretty good estimation of what is the average uncertainty that you have on the state of the system. And so it's a full rank matrix. So it's a good estimation of what should be the B dynamical matrix. But because you like to have some time dependence on B, you really want to account for the fact that the uncertainty on the state of the atmosphere depends on the precise state that this atmosphere has. Then you want to introduce, and especially if you have running an ensemble Kalman filter besides your 3D var, but you'd like to introduce the ensemble of the ensemble Kalman filters to capture some of the uncertainty that could be time dependent. And so they built this hybrid background error covariance matrix, which is just here a linear combination of the static covariance matrix with the one which comes from the estimation from the ensemble. Okay, but of course this one is wrong deficient here. Okay, because there is only a finite number of the ensemble is finite and rather limited, so it only captures some details, and it's also important to get the static background covariance matrix. Also, so what you could do to actually try to avoid some of the spurious correlation that you have in this in computing the empirical covariance matrix here is to apply localization, possibly inflation actually. But you would still get this weighing between the two contribution with this alpha coefficient. Okay, this is something that you have to tune, and to get the best accuracy for your system. And again, you would have, so something more practical would be to have this combination with between the static covariance matrix and the localized empirical covariance matrix, which give you some of the sense of the dynamics for the covariance matrix. Okay, so this is a very nice and simple idea where you start to combine the best of both worlds. So helping a 3D var, okay, with the helping the 3D var with the ensemble of an ENKF. You can also see it the other way around, where you try to use in a ENKF-like scheme some knowledge on some static knowledge on the covariance matrix, but which would be full rank. Okay, so people were focusing, when they try to combine the two, they were focusing on one specific details of the analysis algorithm on the data assimilation algorithm. They were focusing on the background error covariance matrix. Okay, this is one set of algorithm, simple one that you can implement. Okay, it's still useful, and there is another one set of algorithm, which is what we call the EDA, so the ensemble of data assimilation. So suppose you already have this is more from the people coming from the variational standpoint. So people I mean that have implemented their 4D var for their forecasting system, and they want to get some of the ideas from the ensemble Kalman filter, but without implementing an ensemble Kalman filter, without changing their whole system. Okay, so what the idea would be, okay, but let's make several analyses of for instance, my system is based on a 4D var. I invested a lot of time, technical times, engineering times in devising this system. And I want to, I know that my 4D var is not going to give you some time-dependent errors. So I'd like to, at least at the beginning of the window. So I'd like to actually, one thing that I'd like to do to have a sense of, an ensemble of the dynamics that this ensemble provide. I will carry out several analyses. So I will use several 4D var in parallel. So I will use an ensemble of analysis. I will carry out several, the same, but several times the same data assimilation system. Okay, and this is why this is called ensemble of data assimilation. And the idea here would be, so still within this 4D var perspective, you will write the 4D var cost function for one of those analyses. Okay, and that one of these analyses will be an ensemble, a member of the ensemble of those analyses. And of course, you want to generate some new blood. You want to introduce some new blood in those analyses because you don't want them to collapse, like in the Ensemble Kalman filter. So ideally, you would like to, it's not ideal actually, but something very reasonable would be to actually, again, perturb the innovation or perturb the observation, if you want, in this 4D var. So you add some stochastic noise to this innovation in the cost function. Okay, this is generally necessary to avoid the collapse of the ensemble. And the background would be given by, you would start actually not from the previous forecast of the high resolution forecast, but you would actually start from one of the member of the ensemble. Okay, so this would be one cost function for one of the analysis, and you would carry out the minimization of this 4D var for each one of the analysis in parallel. Okay, and so the outcome would be a new set of a new ensemble that you would actually be able to forecast later on. So it's and so that actually when you perform the analysis at the next lab step, you would have an ensemble. You would have, of course, your big error covariance matrix of the 4D var, but on top of that, you would have also the ensemble that maybe you have forecast at the lower resolution, but you will have a sense of this this time dependence of the error, and you could introduce it in the in each one of your 4D var, exactly like you would have done with this hybrid formulation of the background covariance matrix. Okay, introducing some time dependence. And all right, and so this EDA scheme is the one that is actually applied at the European Center, at the ECMWF, and also at Météo France, and it's been also implemented at Environnement Canada and in different forms. But yeah, those ideas were mostly applied in the operational centers where an efficient 4D var was already used. Okay, and another idea is the 4D NVAR. So 4D NVAR is kind of doesn't have an extremely accurate definition, or didn't have one, as opposed to the schemes that I've mentioned earlier. So to the EDA or the hybrid formulation of the background covariance matrix. Here, this is more loose. It's really targeted at the fact, or initially it was targeted at the fact that people in operation centers, that those who operate a 4D var, they really have, they are really wasting time in maintaining the adjoint of the model. I'm speaking essentially of the adjoint of the model, of the numerical forecast model. And so they really want to avoid that, and they want, and as soon as they they develop new schemes in their main forecast model, they want this to be implemented in the adjoint, and so this is extremely painful to update the adjoint. So what they want to do is try to use the ensemble to actually have an estimation of the gradient without using the adjoint of the model. And the idea is really is essentially it's not the same, but it's derived from the fact that you can compute the derivative of any function using the knowledge of the derivative of the function if you already know it, or if you manage to write a code for this function, or you can do just finite differences. Okay, and or of course finite differences are very easy, very convenient. But on the other side, they also are have a limited precision. Okay, you are losing precision when you, and that's the reason why people have computed the adjoint in 4D var, the adjoint of the model in 4D var, to avoid this kind of issue. But so this is in a sense taking one step back and saying, well, maybe if we carry out that in a small ensemble subspace, we can actually compute those finite differences. The goal wouldn't be to compute all the finite differences with respect to each state variable. It would be only to compute the gradient with respect to those coefficients in the ensemble space. So you would have some control onto the accuracy of the finite differences. And so the idea was actually to use this ensemble, so the forecast ensemble, even the one that you have in the ADA, but you would carry out the analysis within the ensemble subspace of this forecast ensemble. So you would forecast the ensemble throughout the next data assimilation window, and that would define a subspace of the set of all trajectory. And then you would optimize on the coefficient of this subset of a trajectory within this window. Okay, so it's this is blending a bit more than the EDA, this ensemble with these ideas of variational optimization. And so now there are many implementations. There are many technical details depending on which operational centers did what. And it was maybe suggested first by Liu et al. On quite a long time ago from a methodological standpoint. And it was tested by Mark Wiener at Environment Canada. And then later on, it was tried by many of the, like the UK Met Office, for instance, it was tried and implemented. Okay, and with the insists the fact that maybe the initial and most important goal was to avoid having to maintain the adjoint of the model. Okay, but one of the drawback, and so there are many papers. There is a very good review by Ross Bannister about those the implementation of those 4D envar methods. And many centers across the world, there are not anymore, you know, the community is not anymore divided into people, you know, pushing the ensemble methods or people pushing the variational method. Now everything is blending together, and maybe on the centers, they are making choices basically mostly on what they already have at hand and how costly it's going to be in time, in manpower, in engineering and in science to actually you know, change that system. Okay, so but one drawback of this 4D envar, it really depends on those technical details, and it doesn't have an extremely well-defined mathematical definition. And the standpoint that I have on the subjects is more it's not, we wouldn't call that, people wouldn't call that mathematical. It's more an algorithmic standpoint, the one that people working on the methods in data assimilation in the geosciences would have. So that's something that you can derive from first principle, and where you don't necessarily control from a mathematical standpoint, but you do have a knowledge of the kind of approximation that you're actually making when deriving the method. And so that I can help you understand actually what the methods are doing and why we are doing this. And so the archetype of that type of method that blend together ensemble method and Kalman filter method is the iterative ensemble Kalman smoother. So let me tell you what they are, and I'm not going to go through the history because that would make us, yeah, that would pick me behind schedule. So I want to first have a view on the time frame on how we are going to, in this scheme, how we are going to assimilate the observations, and where are we going to use the ensemble filtering scheme. When are we going to more use the ideas coming from the variational methods? Okay, so one nice thing about this this scheme is that actually you can have overlapping windows, because usually in 4D var, this is not entirely true, but in 4D var you make a forecast of the size of the analysis window, and then so that you don't assimilate observations several times. But actually, there are attempts to do so by shifting only by half, for instance, the windows. And in operations, you could have some advantages to do so. and to try working on sliding the windows in a slightly different way. But in the iterative Ensemble Kalman smoother scheme, this is very natural to do so. So this is really the standpoint of the Ensemble Kalman filter, and to be very concrete, of the Ensemble Transform Kalman filter. But we want to introduce this sense of a variational window. So here at this time, t minus L minus 2, the present time is this one, and where we assimilate, we are going to assimilate those two observation vectors. Okay, but the analysis will be of variational nature, using the ensemble, but of variational nature, and it will be carried out over this time window. So going into past, and then the product of this analysis will actually be an ensemble. Okay, it's not going to be like in 4D var state. It's going to be a full ensemble. And it will be obtained at the beginning of the window, like in 4D var, you obtain the best the analysis at the beginning of the window, at least if you don't have too much model error. So you do so at the beginning of the window, you got an update, an ensemble. And once you have the ensemble, you will actually forecast, exactly like in the ensemble transform Kalman filter, you will forecast the ensemble throughout the window. Okay, and even going further up to the new present time, which would be here TL, and ready to assimilate new vectors of observations that have been acquired. So those are at time TL minus 1 and time TL. Okay, and then you shift again, and then you carry out the analysis. You got a new update at the beginning of the window, and then you will again make a forecast, and you will effectively you would shift the data assimilation window by this S delta T. So delta T is just the time interval between two vector of observations, and S is by how much you shift the window, and L is the length of data assimilation window in terms of is L delta T. Okay, it's how many delta T you've got in the window. Okay, so it's essentially this method is trying to get the best of what we can get from ensemble method and variation method. The variation method, like for 4D and var, the variation method, the variational analysis is carried out in ensemble space. But then a full posterior ensemble is generated. Okay, thanks to this, and this is something that wasn't done earlier in the 4D and var. And then when you need an ensemble forecast to actually move in time. Okay, so mathematically speaking, this is actually not too difficult. What you want to do is write down like a 4D var cost function. So you've got a sum of discrepancy between the state at all the time step within the window compared to the forecast of the initial state at the beginning of the window with the forecast model, and you've got a background term. Okay, and because we want to carry out like the ETKF, we want to carry out this analysis within the ensemble subspace. We introduce this W coefficient that parameterize the background, so the anomaly the perturbations at the beginning of the window or the prior of the forecast, and you can rewrite the cost functions in terms only of this W vector. And okay, so this is very similar to many of the cost functions that we have already written, with a background which is now written very easily as we would do in the ensemble transform Kalman filter, and everything is hidden into under the carpet, but actually it's explicit here, so you know it's fully compact, but at least you see what you are minimizing with respect to what type of variable you are minimizing. And so you have to optimize over this cost function. And the good thing is that it's the set of W coefficient is limited because it's the size of the ensemble, without considering localization for now. Okay, and there are on-the-shelf methods in applied mathematics to actually minimize this cost function. You can actually use a numerical method on the shelf directly, or you can use a very standard, very efficient mathematical method, which is called the Gauss-Newton method. Okay, I'm sure most of you has already known already the Newton-Raphson method, and this one is a simplified case when the loss function or cost function to minimize is composed of square. So this is a simplified way, and it's easy to compute. So you can explicitly write the gradient of J, and hence you can build an update for the when you minimize over this linear loss function. You proceed by iteration, like for any nonlinear loss function. And you've got an update that depends on P, and P is the loop iteration, is the iteration of this minimization. And you sequentially update this set of coefficients until convergence to find the minimum of the loss function. Okay, and it requires the computation of the gradient, as we said, so the gradient of the loss function. Okay, you don't have to necessarily look into the formula, but it just implies, the ensemble. This will apply to use the ensemble, the observations, and the nonlinear forecast of the model within the window, exactly like for the NVAR. Okay, so it's all these is just ingredients that we have already seen. It's just okay, put together in the condensed form. The nice thing about it is that here we are relying on the, you see, on the transpose of a matrix and not on the adjoint of the model. So we are actually making an approximation here, like a finite difference approximation, where we compute the gradient in a trivial way using the model, using the ensemble, and not the model, the numerical model. Okay, so this is just, this hides just the fact that you are computing finite differences. And things now you've got, once you've got the minimum of this loss function, you just do exactly like for an ETKF, you do just an update like you would do for an Ensemble Kalman filter. Exactly the same, okay, except that like for the 4D ETKF that we've seen earlier, you're actually using observations coming from different time from within this window. But the and then the perturbation update is written exactly like we would do in within an ETKF, and then we would have to forecast, make a forecast, and it's not a one-step forecast like an ensemble filter Kalman filter. It would be like many steps forecast, because we want to forecast within the window plus moving forward in time. But aside from this, this is very, very similar to the ETKF. Okay, and one thing I should mention, maybe you've heard, we will heard this actually generalize one method that has been introduced by Zupansky almost 20 years ago, which was called the maximum likelihood ensemble filter, which was an ensemble transform Kalman filter, but where we would like to account for the fact that the observation operator could be nonlinear. And so you can see that the iterative ensemble Kalman filter or smoother, I use both terms, filter or smoother, it's actually a generalization of this maximum likelihood ensemble filter. Okay, and for the ETKF is also can be seen as one iteration of the iterative ensemble Kalman smoother. And it turns out that depending on the exact implementation, 4D and VAR can also sometimes be seen as also a subcase of this iterative ensemble Kalman smoother. Okay, I'm not discussing this. I just want to show you the numerics again using the very simple Lorentz 96 model, and it's so nice because now we can compare that to the method to the ensemble transform Kalman filter, and see what those iterative ensemble Kalman smoother or filter brings to the game. So this is the filtering now. So this is the score of the system at the beginning of the window, okay, lag 0 at the present time. We want to see what are the scores. And the ensemble Kalman filters will give you, and it was actually the same value that I showed earlier, will give you this score, so about 0.20. And if you go in the past, because you're using an ensemble Kalman filter, you don't make any improvement. You don't make the second pass of the ensemble Kalman smoother. Yeah, or if you make the second pass, I mean, sorry, it's not an issue because here we are only considering the filtering, so the score at the end of the window. even if the window is bigger, okay, even if you use the Ensemble Kalman smoother that we've seen with a big time window, a lag which is large, if you look only on the scores at the system at the end of the window at present time, then of course you still get the performance of the Ensemble Kalman filter. So this is this curve in yellow or orange, depending on the monitor. Now, if you use the 4D var, and even if you use optimally, okay, by tuning some of the coefficient, you would end up, so changing the length of the window of the 4D var, you would end up with these violet curves. So you see, Ensemble Kalman filter and 4D var are not mathematically equivalent at all, okay? They lead to different results for reasons that we understand, because 4D var is not as good here on this toy model for short window, because it doesn't have this sense of the dependence of the error on time. Okay, so this is really hampering the 4D var for short time window. But when you move to longer window, then 4D var has a better sense of the dynamics, and it implicitly propagates the error within the window. It never writes it, it doesn't never outputs it explicitly, as opposed to the NKF, but it does implicitly assume this. So at some point, 4D var has this knowledge of the time dependence on the errors, and it also now can probe the system in a nonlinear way, because it can do the minimization in a nonlinear way, something that the Ensemble Kalman filter cannot do. Okay.
Professor Mark.
Yeah.
10 minutes. Okay.
Yeah. That's good. So that's the this explains the difference between those two curves of the well-known methods. But if you look at the this prototype of what should be an ensemble variational method that brings the best of both worlds, you see that, and only look at the green curve. Don't look at the other curves that would be some variation about it. So if you look at the green curve, this is typically what the iterative Ensemble Kalman filter or smoother can give you. And since it has an ensemble, it captures the errors of the day, okay, the dependence in time of the error. But since it's also variational, and it can probe the non-linearities of the model, okay, which is better than the Ensemble Kalman filter. So as you get to longer window, it also gets what the 4D var can get you. And that's why you've got a curve that is actually better than 4D var and the Ensemble Kalman filter altogether, and even Ensemble Kalman smoother. Okay, so you really get the best of both worlds in this case. If you look at the smoothing analysis, so the smoothing is here. It's I'm looking at what I can do at the beginning of the window, so in the past, with some lag, and so using those feature observation. That will be for reanalysis. And you've got again similar curves, except that the ensemble smoother is doing better, as I explained at the beginning of this lecture. But they are again crossing, and again the iterative Ensemble Kalman smoother, the green curve, is doing better than those two set of systems of a data assimilation method. Okay, so I'm not going to discuss this. Those are variations onto the iterative Ensemble Kalman filter or smoother. I'd like just to mention, maybe to finish this, that you can also, and this is something more delicate, but you can also incorporate model error into the scheme, on top of the fact that there is an ensemble, that there is a nonlinear 4D variational aspect of it. You can also incorporate model error, at least in the classical way, that the way we do that in the weak constraint 4D var. And this is implementing. This is the example on the one lag smoother. So this is called the iterative Ensemble Kalman filter. And it turns out that again, this actually in this case, this can be also very nice, because again, you can write the full loss function, the full cost function, as something very similar to all the cost functions that we saw before. And in particular, this is formally exactly the same cost function as the one that we have in the iterative Ensemble Kalman smoother. Okay, and actually the ensemble, the model error is completely hidden under the carpet, and it's not an issue because now you can reuse completely the algorithm of the iterative ensemble Kalman smoother, and you can reuse the code with some small modification, and you can actually account for model error, which is nice. Or for some types of specific type of model error, because model error can be more difficult. Okay, so this is some scores, but I don't want to discuss that. Okay, this was from a theoretical perspective. It's this ensemble smoother is ensemble Kalman filter, iterative ensemble Kalman filter or smoother is nice because this is really, you really can write down the equations that you would require to merge in a consistent way an ensemble method with a variational method. And that's, even though you don't necessarily have to use this method, you can always go back to the method and make a comparison and have maybe a better view on the method you are developing. Okay. So essentially, to summarize, whoops, where is the... Okay, to summarize, we've seen there was a brief recap on the NKF. Then I wanted really to tell you that some of the smoother that were developed quite early were actually a first step towards merging those two sets of techniques. And then I described some of the main well-known techniques without going into the implementation details, but they were those techniques. We emphasize that this hybrid was mainly used initially for the covariance matrix. But then there is this EDA, which is still used in which is very successful and used in several numerical forecast centers. And there is this 4D ENVA, where we want to use this ensemble as a framework to perform to carry out the optimization of a 4D VAR. And then there was I showed what was a nice, consistent, and derivable mathematical framework to understand how to blend things together, and it actually shines back onto the other method because it brings or sheds light onto the other methods. It explains why they are successful or not. And at the end, you see a lot of references. So I haven't updated this bibliography over the past 3 years on those topics. So I'm pretty sure there are very nice papers on the topic over the past 3 years. But I guess you've got a lot of them, nice papers on the subject that I've listed at the end, at least up to 2020. And that's it. Thank you very much.
Thank you. Thank you very much for this amazing talk here. This is you. By the way, we have some questions in the chat. Okay, and Professor Mark talk about a Kalman filter, different approach for ensemble Kalman filter, variational methods, and how can we combine these two strong techniques. Thank you, thank you. And I would like to mention that Professor Mark has a book. This is from American Society for Industrial and Applied Mathematics. The title of his book with two other colleagues, Data Assimilation, Methods, Algorithms, and Application. I recommend it strongly to all people interested in data assimilation to consulting the book, so you can get more information about data assimilation. Please, if you can address some answers for the questions.
Yeah. Let me see. Okay, tangent linear model from TK. Okay. Yeah, maybe it's too late for this one, but I'm going to be back. I'm going to go back. Yeah, okay. I have understood that smoothers methods can be very useful to generate reanalysis. Yes. Do you think they can also be useful to improve forecast in the context of operational case? So if you use it's a subtle questions, and that's something that that actually we've worked on. It's so the answer is yes, but it's not obvious because if you use the Ensemble Kalman smoother, not the iterative one, if you use the Ensemble Kalman smoother that I described, then you've got only two paths. So one path forward in time, and one pass backward. And backward, so it will only help you in the reanalysis. It won't help you to have a better forecast. Okay, but if you use the iterative ensemble smoother, for instance, in principle, and this is actually seen in the curves that I've shown, you can, even if you go back in time, then you can make a better forecast from it, because you don't only make 2 passes. Implicitly, you make several passes through the minimization. Okay, so the answer is yes. Okay, how about the complexity for steepest descent Gauss-Newton scheme for large systems? So the here the idea it's actually fine, because the you do that in the ensemble space. Okay, and it's typically 50. So it's fine. Per se, it's fine. The price that you have to pay that I haven't spoken about is that, like, the only actually drawback that all those methods, ensemble variation method, have, and there is only one from a mathematical standpoint or numerical standpoint, is the fact that you still need localization, because you still have a finite, a limited size ensemble. So you still need to use localization, and because of that, that could be this is still the tricky part actually that you have to implement. So yes, this is not an issue to use Gauss-Newton, but remember that you have to move from this finite representation of the ensemble to something which is localized. So in this, in the context of the ETKF, you would have to make several analyses like in the LETKF. But no, it's not an issue here. If I go back, if I understood, it was both each member has a different first guess. And also, whatever observation receive a white, not perturbation. Okay, so this is in the case of the that would be like for the stochastic ENKF and also for the EDE. Why should both the background and observations vary between ensemble members and not just one of the components? Well, that's something that you can actually check on the just on the linear, without considering a difficult nonlinear system. You can check the statistics using a very trivial, simple linear model, and you can carry out the statistical analysis and see if the posterior error is the one that you would obtain from a simple blue analysis or a simple Kalman filter analysis. And it turns out that you have the proper uncertainty. You need to account for the errors in the background. Okay, this is for the forecast. This is accounting for the forecast error or the prior error, and you need to account for the errors in the observations by perturbing the observations. So you need to account for both. If you only account for one, you will collapse at some point. But now I don't want to impede too much on the on Peter-Jan's talk.
Yes.
So maybe there are questions that I will be able to answer while listening to Peter-Jan.
Okay, if you can email to Professor Mark if you have other questions, and I'm sure that he is available to go back to the answer for you.
And I will answer some of the other questions in the chat.
Okay, thank you a lot for to accept of our invitation. That is one amazing talk, as I said. Merci beaucoup. Thanks a lot.
Thank you, Aldo. Thank
So
you.
let's move on to the next speaker. Thank you.
Yes, thank you. And Peter, may you put your slide?